So now I am going to start my topic, that is haloalkanes, and it is simply also known as alkyl halide. So for the haloalkane, we should first know that is alkane, and it is the simplest alkane, which is known as methane, in which carbon atom is bonded through four hydrogen atoms. So when one or more hydrogen atom of these alkanes are replaced by halogen atom, that is fluorine, chlorine, bromine, or iodine. When one or more hydrogen atoms of these alkanes are replaced by halogen atoms, then this one, when this hydrogen atom is replaced, any one or more, then this is well known as haloalkane or alkyl halide. So now alkyl halide or haloalkane can be classified. This is the simplest one, that one or more hydrogen atom can be replaced or substituted by halogen atom, that is fluorine, chlorine, bromine, iodine, and the resultant product is well known as haloalkane or alkyl halide. So now coming to the classification. Classification first is based on the number of halogen atoms, and second one. So now first I am explaining the number classification based on the number of halogen atoms. So this is the first, I am taking the example of methane. When one hydrogen atom is replaced by any halogen, that is resulting in this one. So this is well known as mono substituted. Mono means one substitution takes place. And when two hydrogen atoms, this one and this one, is replaced by two halogen atoms, so this one and this will be di-substituted. And similarly, when three hydrogen atoms are replaced by three halogen atoms, that is this one, so this is known as tri-substituted. And when all the four hydrogen atoms of this alkane is replaced by four halogen atoms, that is this one, so the resultant product is well known as tetra-substituted haloalkane. So based on the substitution of protons or hydrogen by the halogen atoms, the haloalkanes are classified in four groups, that is mono-substituted and di-substituted, tri-substituted, and tetra-substituted. So now the second one, classification, which is based on the carbon atom, and as we know, carbon atoms has four types. So this one is primary carbon atom, because this carbon is attached to only one carbon atom. This is secondary carbon atom, because the main central carbon atom is attached to two carbon atom, and this is primary, this is secondary, and this is tertiary carbon atom. So when halogen atom is attached with primary carbon atom, this is known as primary haloalkanes. And when a halogen atom is attached with the secondary carbon atom, that is secondary haloalkanes. And when halogen atom is attached with tertiary carbon atom, that is carbon atom attached to three carbon, so this is known as tertiary haloalkanes. So these are main two classifications of haloalkanes or alkyl halide. That is first one I already explained, that is based on the a number of substituted halogen atoms, and second one is the classification based on the carbon atom, that is primary haloalkane, secondary haloalkane, and tertiary haloalkane. So now moving towards the other points, which is the most important, that is the nature of CX bond. That is nature of CX bond in haloalkanes. So this is the very simple haloalkane, that is methyl halide or halomethane. It is also known as halomethane, and we can see that there is a bond between carbon and halogen atom. Halogen atom may be fluorine, chlorine, bromine, iodine, anyone. So as we know that all the halogen atoms are highly electronegative. Highly electronegative compared to the carbon atom. So they will withdraw the electrons of this bond towards themselves. That is, halogen atoms will withdraw the electrons, and resulting in the partial positive charge to this carbon atom and partial negative charge to halogen atoms. So this bond between carbon and halogen atom, that is CX bond, becomes polar. So the haloalkanes, in haloalkanes, the CX bond becomes polar, and leading to a series of chemical reactions and other tuning physical and chemical properties. So based on this polarity or the nature of this CX bond, which is caused by the electronegativity of halogen atoms, we can explain more other properties of the haloalkanes. That is, first we should know that fluorine, chlorine, bromine, iodine. In periodic table, the electronegativity will increase from bottom to top. That is, fluorine will be most electronegative. Fluorine will be most electronegative, and the size of halogens will increase from top to bottom. So when talking about the fluorine atom, which is attached to carbon atom, due to higher electronegativity in halogen atoms, this bond length will be very shorter, because this will withdraw electrons very strongly, and the attraction force between carbon atom, del positive and del negative, will be high due to its high electronegative atom, and these both atoms are will be very close to each other, leading to the very shorter or low bond length for fluorine. That is, shorter or low bond length means this bond length will be very shorter and they will be very close to each other. This is the another factor is there, because the size of fluorine is very low. So this is the another factor why the bond length is shorter. So when going to from bottom to top, due to the high electronegativity, the bond length will be shorter, and for this one, when this will be iodine, the bond length will be higher or longer for Ci1. So the first property can be explained that the bond length between bond length of the CX bond, for here I am writing for CF, CCl, CBr and Ci, this has very shorter bond length and Ci will be longer bond length. So this is the main property, and I already explained that why CF bond will be very shorter, because fluorine is very high electronegative, and when fluorine is here, the bond length will be very shorter due to the high attraction force between del positive and del negative carbon and fluorine. So the Ci bond will be very longer and CF bond will be very shorter, and from this is the bond length. We already know that shorter bond length will be very stronger, because they will be very close, both the carbon and halogen atoms. So shorter means the bond will be very stronger between CF, and very weak between carbon and iodine. So when bond will be stronger, the energy required to break these bonds, CF, Cl, Cbr, the stronger will be the bond and the energy will be higher to break the bond. So as we can write that bond length will increase from Ci to Cf, and Cf will be very high bond length, very low bond length, and bond will be stronger due to the closure of this carbon and fluorine atom. So as I explained that a stronger bond will require higher energy to break these bonds. So when these bonds will be break, the due to the strong bond enthalpy, it will be higher bond energy, that is CF, carbon and fluorine bond will require higher energy to break this bond. Similar, CCl, CBr, Ci. So it will be this one, increasing order. So as the bond CF has the stronger bond, so the bonding energy or bond energy to break the CF bond will be higher, and the bond energy will increase from Ci to CF. That is, CF will require higher energy or higher bond enthalpy. It is also known as bond enthalpy for the breaking. And Ci bond will require very low bond energy to break the Ci bond. So it is known as the CF will have high bond enthalpy and Ci will have low bond enthalpy. So now, after explaining the nature of CX bond, the most important topic of the haloalkanes is the substitution nucleophilic reaction, that is also known as SN reaction. In substitution nucleophilic reaction, the halogen atoms are replaced by other nucleophiles. That any other, I am writing this is Nu minus. So attack of nucleophile takes place on haloalkanes, leading to the formation of a new product, and the halogen atom will be removed. So this simple reaction is well known as the nucleophilic substitution reaction of haloalkanes, in which halogen atoms is replaced by nucleophile and leading to the formation of a new product, and the removal of halogen atom takes place. So we can divide the nucleophilic substitution reaction in two groups. That is, first one is known as SN1 reaction, that is full form is substitution nucleophilic unimolecular. This one means, unimolecular means that rate of reaction is dependent or directly proportional on only substrate, only one, either substrate or nucleophile. So in SN1 reaction, that is rate of reaction is depend on only substrate, that is haloalkane. So it is known as substitution nucleophilic unimolecular reaction. So this reaction proceeds through carbocation mechanism and divided into two steps, first and second. In first step, as I am writing the mechanism, this is the well known tertiary haloalkane. In first step first, this bond is breaked, and leading to the formation of a carbocation, that is tertiary carbocation, and removal of nucleophile. This is the very slowest step, and as we know that slowest step is the rate determining step, and the rate of reaction depends upon this, that is based on only substrate. Here is no involvement of nucleophile, and this is well known as substitution nucleophilic unimolecular reaction, in which rate of reaction depends only on the substrate. that is tertiary haloalkane. So in first step, in first step the tertiary alkyl halide or tertiary haloalkane go through dissociation, and the breaking of this CX bond takes place, leading to the formation of tertiary carbocation. And in second step, this tertiary carbocation CH3 reacts with nucleophile, or nucleophile attacks with this tertiary carbocation, leading to the formation of new product, that will also be tertiary. So this is the total mechanism that so total mechanism of SN1 reaction, that is first step involve the dissociation of CX bond, leading to the formation of tertiary carbocation, and after that in second step the nucleophile attack takes place on tertiary carbocation, leading to the formation of a product. So just when there is also a stereochemistry behind this reaction, as we know that the tertiary carbocation, as I am writing, is trigonal planar, this type of geometry have. So in second, I am explaining just only second step. So nucleophile attack of nucleophile is possible from front side and also from back side, this one side. So this is only trigonal planar system, and the nucleophile attack may be possible from front side and back side. So two type of product is possible based on the geometry of carbocation. That is, when front side attack takes place, the nucleophile will attach from this side, and when back side attack takes place, the nucleophile attacks from the back side, leading to the formation of this type of geometry. So when front side attack takes place, that is this one. This is known as retention of configuration. And when backside attack takes place, this is known as inversion of configuration. So there is possibility of 50% possibility that 50% attacks takes place from front side and 50% from back side, and these two products are formed based on the geometry, that is called as retention of configuration and inversion of configuration. Completely this is known as racemization. So when a reaction give 50% two products that is opposite to each other in configuration, that is retention of configuration and inversion of configuration, this process is known as racemization. So this is overall geometry and overall mechanism of the SN1 reaction. That is the most important is that SN1 reaction mostly give the racemic product, leading to the formation of retention as well as inversion of configuration of the molecules. So now coming to the second type of mechanism, that is known as substitution nucleophilic bimolecular. So similar to the previous one, rate of reaction here will depend on substrate as well as on nucleophile, that is Nu minus. So rate of reaction depends on both substrate and nucleophile. So this is known as substitution nucleophilic bimolecular reaction. And the main important point of this mechanism is this is a concerted mechanism, that takes place only in one step. In only one step, and I am drawing the mechanism. Or we can draw this type of mechanism. Simple methyl halide and nucleophile. So in concerted only one step mechanism, this nucleophile attack takes place, but due to the presence of nucleophile from front side, the back side attack is mainly possible. So in this step, a transition state is formed in which back side attack of nucleophile lead to the slight formation of bond with carbon atom, and front side the leaving of the removal of halogen atoms takes place. So there is a transition state takes place in which nucleophile attacks and a bond formation between carbon and nucleophile, simultaneous bond formation of carbon nucleophile and bond breaking of carbon and halogen atom takes place. So this is well known as transition state, in which carbon is also well known that it is penta coordinated or pentavalent. So further, this nucleophile is attached from back side, and the halogen atom will be removed. So for the back side we can draw from similar to that is CH, H and NU. So in this concerted mechanism, the backside attack, in 99% chance of the backside attack is possible, and as we can say here, halogen atom is attached from front side, but the nucleophile after the reaction is observed on back side. So it is totally well known as inversion of configuration, because I already explained that backside attack leads to the inversion of configuration. So in comparison to both, the SN2 mechanism will give only the inverted product, that is the inversion of configuration due to backside attack, and it is the mainly one step concerted mechanism in which a transition state takes place, in which carbon atom is attached with nucleophile as well as halogen atom. So finally SN1 and SN2, SN1 proceeds through carbocation mechanism, SN2 proceeds through transition state, and carbocation mechanism gives racemization, and this transition state mechanism gives inversion of configuration.